We are going to skip example number 3 because I was not able to correct the typing which I do using there's some problem with the file, but anyway. So whenever I can do that, then I will get back to it. So we move on to example number 4. So example number 4 reads as follows. Pulled by the 8 Newton block shown in figure 4, which is this one here, in figure 4, the 20 Newton block slides to the right at a constant velocity. Okay, so pulled by the 8 Newton block shown in figure 4, the 20 Newton block slides to the right at a constant velocity. Find the coefficient of kinetic friction between the block and the table. Assume the pulley to be frictionless. So what we have here again is an example of what we mean when we talk about equilibrium, especially the fact that we mentioned that equilibrium has got two types. There are two types of equilibrium. There is one where an object does not move. That is what we referred to as static equilibrium. There is another kind of equilibrium where an object moves, but this particular object moves at constant velocity. So if an object is moving at constant velocity, then it is experiencing a type of equilibrium which is referred to as kinetic equilibrium. The common thing with both of these types of equilibrium is that the resultant force, when you add up all the forces acting on these particular objects, this 20 Newton object, when you add up all the forces acting on these 8 Newton objects, the resultant force adds up to 0. So there is no acceleration. So whenever you have got equilibrium, you do not have acceleration. If you do not have acceleration, then one of two things are happening. Either the object you're looking at is motionless, it's not moving, or the object you're looking at is moving, but it's doing so at constant velocity. So the first thing we have to do is we need to identify what kind of forces are acting on these particular objects. What forces are acting on these particular objects? As you can see from this figure, this particular object is 20 newtons. This 20 newtons is the weight of this object. Are we clear? The 20 newtons you have here is the weight of the object. The 8 newtons you have here is the weight of this particular object. So these 8 newtons and the 20 newtons, these are weights. And as we have always seen, as we know, the weight of an object always points down. So the weight is pointing down like this. If I don't have something which writes, but I think if you have printed the notes, you can indicate that the weight is pointing down like this. The weight of this first object is pointing down like that. If the weight of the object is pointing down like this, then this object is exerting a force on this surface. So this surface is also pushing back upwards. So the weight of the object is pointing down, then this surface is pushing back against the weight of this particular object. Is that clear?
Yes, sir.
That is just Newton's third law of motion. If you have a force, like in this case, 20 Newton's force acting on a surface, that surface is going to react and it's going to exert another force on the other surface which is equal but opposite. So this 20 Newton weight is acting on this, in this downwards, pointing downwards. It's exerting a weight on the table. This table is pushing back upwards with a normal force. So those are the first two forces you have to identify. When you look at weight, when you look at this, When you look at an object, you have to identify that this particular object has got weight. So you indicate on your notes that there's weight pointing down. Then there is this table pushing back against this object. The other thing is, of course, you can see that this particular object is being pulled by this rope. So if this object is being pulled by this rope and the tension in this rope is Ft2, is being pulled by this rope, so this object is moving in this direction because of the fact that it's being pulled by the rope. When this object is moving in this direction, there is going to be opposition which this object is going to face. So there's going to be friction pointing in the opposite direction, this side. So you have the weight of the object pointing down. You have got the table pushing back against this object, which is up. Then you have got the tension pointing in this direction, pulling this particular object so that it moves at constant velocity in this direction. Then you have got friction, which is trying to stop this object from moving, which is pointing in the opposite direction. So basically, you can put an XY plane. You can draw an XY plane on this particular box like this, where this side, the direction in which the object, when you draw an XY plane on the surface, we usually choose the direction in which the object is moving to be the x-axis. So in this particular case, if you draw your XY plane like this, so this direction in which the object is going to be moving, this is going to be your positive x-axis. The other direction, this side, is going to be a negative x-axis. Up that side is going to be a positive y-axis. Down this side is going to be your negative y-axis. So with this object, the 20 Newton objects, we have identified 4 forces which are acting on this object. There is the weight of the object, which is 20 newtons. There is a normal force which is pushing up against the object, which should be equal to the weight of the object. There is a tension in this rope, which is what we have here. There is also the friction force, which is trying to pull the object in this direction to stop the object from moving. So that is what's happening to this first object here, with all those forces acting on it. The other object of interest is this one, the 8 Newton object here. This is the other object of interest here. In this particular case, this 8 Newton object, the weight of this object is pointing down here. So there is a weight of the object pointing down in this direction, down like that, because weight always points down. However, as this particular object is being pulled down, there is also this string which is connected to this particular object. This string is trying to push, is trying to pull the object up. So the string, as it's trying to pull the object up, is basically slowing down how fast this particular object is falling. That's why the object is falling at constant velocity. It's not accelerating because it's being pulled by the string. Are we clear? There is this weight. This particular object has got weight also, so the weight of this object is pointing down. That's the reason why this whole thing is moving, is moving in this direction. So there is a weight which is being exerted by this particular object, but as it's doing that, this object also is being pulled up by this rope. This section of rope. This section of rope is pulling the object up. That's why there is no acceleration. Are we clear?
Yes, sir.
Yes, sir.
So, when you look at this particular object, there are only 2 forces acting on this 8 Newton object. There is a weight of the object pointing down. There is a friction of the object. So there is a weight of the object pointing down. There is also the tension in this rope, which we are calling Ft1. This one, the tension in this rope is pointing up. Now, you will notice one thing. This is the same rope which passes through a pulley, passes over a pulley. It is the same rope passing over a pulley. But depending on which side of the pulley you are, the direction of the tension, in this case, this side of the pulley, the tension is pointing up. So you indicate, if you have printed your notes, you indicate that this tension is pointing up. This side, the tension is pointing this particular direction. So when a rope goes over a pulley, the tension in the rope, both on either sides of the pulley, the tension in the rope will be in opposite direction. It will be pointing in opposite direction. However, because it is the same rope, the tension, as much as the tension will be pointing in opposite direction, the tension will have the same size. The size of the tension will be the same. That's one thing you're supposed to be aware of. When you have a rope going over a pulley, the whole rope has got the same size of tension. The force which is generated in the rope, which is the tension, will be the same. The difference will be where the tension is pointing. On this side of the pulley, the tension will be pointing in this direction because it's pulling the box in this to move in this direction. On this side of the pulley, the weight is pulling this mass down, but the tension in this rope is pulling up. Are we clear?
Yes, sir.
So on this particular object, the 20 Newton objects, you can draw your XY plane over this object. Then you can also draw your XY plane over this object. So when you identify an object which you're looking at, in this case, we've got two objects we're looking at. The 20 Newton objects, you can draw an XY plane over it. This one also, you can sketch an XY plane over it. You notice that in this particular case, the only forces which are there are only in the y-axis. There are no forces acting along the x-axis for this particular object. So there are only two forces: the weight of the object down and the tension of the rope pulling the object up. So you sketch. That's why I've asked people to print these notes. You print out the notes so that as we are discussing, you sketch, okay, fine, so this is what I do, this is what it looks like. Because right now, as they are, I still probably need to make corrections to these notes, but time is not really with us, so those corrections and the putting of the x-axis over them will not happen this year. It will probably happen next year. Okay, so with that information, for this object, we have identified four forces. For this object, we have identified two forces. For each of the objects, we create what's this? Table of components. We create a table of components for each of the objects. So this is a table of components for the 20 Newton object. For the 20 Newton object, you notice that for the weight, in this particular case, the weight of the 20 Newton objects, which is Fw, along the x-axis, there is no weight. There is no component, because the weight is only, if you do you put an XY plane here. So you put an XY plane here like that. So you notice that the weight is in this direction, down here. So along the x-axis, the weight, and if you put your XY plane over here, this is going to be a positive x-axis, then the weight is going to be pointing in this direction. In this direction. So along the x-axis, your weight is going to be at an angle of 270, like that. So if the angle is 270, if you work out what this is here, you work out what we have here. Actually, I've even made a mistake myself. So you work out the weight, which is 20. So you're saying right somewhere on top here, 20 newtons cos 270. So up here, so that you get this 0. So you write 20 newtons cos 270. That should give you 0 newtons. But if you do 20 newtons sine 270, that should give you minus 20. So this 20 which you have here is supposed to be minus 20. Are we clear? Is it clear?
Yes.
Remember, when you identify the object, you draw, you sketch, you're supposed to sketch, you draw an XY plane over this object. When you draw, you sketch an XY plane over this object. This side is going to be your Y, this side is going to be your X-axis, like this. So this side is going to be your positive X-axis. This side will be your positive X-axis. So if the weight of this object is down this way, then the angle from the positive x-axis, as we go around like that, the angle is going to be equals to 270. So the angle which the weight makes from the positive x-axis is 270. The angle which the normal force makes from the positive x-axis is 90 degrees. the angle which this tension makes from this positive x-axis is 0. The angle which the friction is going to make from this positive x-axis is going to be 180 degrees. So even in this thing, because of this failure to, the file is failing to, there's some mistakes in how it's failing to compile. So I just need to explain it so that you can correct things like that side. So like we've said, the x component, that's going to be 20 newton up here on top of this. So you write with a pencil or whatever your pen you have, 20 newtons cos 270. That's what's going to give you 0 degrees. Then up here above the 20, you write 20 newtons sine 270. When you do that, 20 times sine 270, you are going to get a minus 20. So this is supposed to give you minus 20. Then the normal force. The normal force is the reaction which the table is going to push against the box. So when the table pushes against the box, the normal force is going to be pointing up. When the normal force is pointing up like this, and you have your xy plane, so the angle from this positive x-axis to where the normal force, that angle is going to be 90 degrees. So in that case, your normal force is going to be equals to whatever your normal force is. Your normal force, Fn, so up here you write Fn, on top of this, you write Fn cos 90 degrees, that's going to give you 0. Then here on top of this, you write Fn sine 90 degrees, that's going to give you Fn. Are we clear? Are we clear? Okay, then if you look at the tension in the rope, because you have drawn an XY plane over this particular box, you have drawn an XY plane over this particular box, the tension in the rope will lie along the positive x-axis. So this force makes an angle of 0 degrees with the positive x-axis. So in that case, the angle for the tension in the rope with the x-axis is 0 degrees. So you're going to have Ft2, which is the force, the vector force. Yeah. So you're going to have, on top of this one, you write Ft2 cos 0 degrees. That's going to give you Ft2. Then here on top of this, you write Ft2 sine 0 degrees. You're going to get 0 degrees. Are we clear? So make sure that this 20 is minus 20 here. That's minus 20. Then when it comes to the friction force, you notice that the friction force is at an angle of 180 degrees from what we have chosen to be the positive x-axis, this side, this direction. If you draw your xy plane over here, then you choose the positive x-axis to be the direction in which the box is moving. So there's going to be an angle of 180 degrees, and the friction force is acting in this direction. So when you do that, so you can work out what the friction force is going to be. So the friction force, in this particular case, you're going to have, for friction, you're going to have the friction force, Ff, cos 180 degrees, and that's going to give you minus F. Are we clear? Ff cos 180 degrees is going to give you minus F. So this one is supposed to have a minus in front of it. Is that clear? Yes, there's an excuse. Go ahead.
Yes, there are some people that are to be admitted.
Oh, okay, okay.
There are some people.
Okay.
All right, thank you.
Yeah. So there's supposed to be a minus in front of here. So there's supposed to be a minus in front of the 20. There's supposed to be a minus in front of the F. Then when you work out the y component of the friction force is going to be Ff sine 180 degrees, and that's just going to give you 0. So the corrections here are, in front of the 20 here, there should be a minus. In front of the friction force here, there should be a minus. Is that clear? Are we clear?
Yes, that's clear.
Next, so with that, you can add Remember what it is we are talking about. We are saying that there's, when we add all the forces along the x-axis, 0 plus this plus what, this is being positive force, this is a negative force. When you add all of these, they should give us a 0. When you add all the forces along the x-axis, they should give us a 0. When you add all the forces along the y-axis, they should also give us a 0. So when you do this calculation, when you do the addition, where have we tried to do it? Here. We're adding the sum of the forces. When you add the forces along the x-axis, you should get a 0. So in that case, we're going to have 0 newtons plus 0, the other 0 newtons plus this bit. But this one here, like you have said, it's supposed to be negative. Here, from the table. This, when you're adding the forces along the x-axis, 0 newtons plus 0 newtons plus Ft2, this is supposed to be negative. Are we clear? So when you do that, what you end up with will be the following. So make corrections on the notes. So we're adding all the forces along the x-axis. So you've got 0 newtons plus another 0 newtons plus Ft2 plus minus F equals to 0. So when you do that, you end up with this guy. So this one has got a minus in front of it. You're going to end up with F being equals to Ft2. So this negative must go. So you cancel out the negative there. Are we clear?
Yes, sir. Yes, sir.
That negative needs to go. So please make an effort, print the notes. Okay. So we have the friction force is being equals to Ft2. Okay. Then we move on to the other side, the y side of this table. When you move to the y side of the table, remember there is a negative in front of this 20. So this is negative 20 plus Fn plus 0 degrees plus this whole thing. According to our first condition of equilibrium, all this should give us 0. When you add them up, we should end up with a 0. So when you do that, this one, the 20, is supposed to be minus 20 plus Fn plus 0 should give us a 0. So at the end of the day, when you do that, we end up with Fn equals to 0. Sorry, Fn equals to 20. Remember, this is, you put a negative in front of the 20 there. So put a negative in front of this 20. So you have minus 20 newtons plus Fn plus 0 newtons plus 0 newtons equals to 0. So we end up with Fn equals to 20 newtons. Is that clear?
Yes, sir.
Okay. Then we move on after. That's all we can do with the first object, because the first object is just moving at constant velocity. That's the only thing you can do. Then we move our attention to the second object, which is this 8 Newton objects. With this same 8 Newton objects, you draw an XY plane over it. XY plane over it. So since we placed an XY plane over this other one, we draw another one over this one, like this. Then we choose this direction to be our positive x-axis. The other direction will be our negative x-axis. Then we notice that there is a tension in this rope. So the tension will be at 90 degrees. So this tension will be at 90 degrees. Then the weight of the object will be down. So that weight of the object will also be at 270 like previously. So the tension in this rope will be at 90 degrees. The weight of this particular object here will be at 270 degrees. So we can work out the components of this particular object. And that's where this other table comes in. So the weight of the object here. So the weight of the object in this particular case is going to be the 8 newtons. So 8 newtons times cos. So right on top of this. So the angle of the weight from the x-axis is positive x-axis is 270. So on top of this, you write 8 newtons cos 270. That's going to give you 0. Then on top of this, you write 8 newtons sine 270, that's going to give you minus 8 newtons. Are we clear?
Yes, sir.
Yeah. Then when it comes to the tension, so along the x-axis, so if you want to work out what the tension is, so it's going to be what FT1, the tension makes an angle of 90 degrees with the x-axis. So FT1 cos 90 degrees, that's going to give you a 0. So you put a negative. Then when it comes to this other one, FT1 sine 90 degrees, that's just going to give you FT1. So as you can see, along the x-axis, the components are 0. So if you add up the components along the x-axis, they're just 0. But along the y-axis, you have got a minus 8 newtons, you have got an FT1. These are the components along the y-axis. So we add up the components along the y-axis in this particular case. When we do that along the y-axis, like this, when you enforce the condition of static equilibrium along the y-axis, we're going to end up having it's minus 8 newtons plus FT1 equals to 0. So if this is minus 8 newtons plus FT1 equals to 0, then you're going to end up having FT1 equals to 8 newtons. So this negative needs to go. So make that correction. So FT1 is equals to 8 newton. So this is what we have now. So what we have is the following. We know that Fn, the normal force, is equals to 20 newtons. That's what you found. The normal force is equals to 20 newtons. We have also found that the friction force is equals to Ft2. That's what we know here. The friction force is, so this one, Ft1 is equals to 8 newtons. So the negative should go. We have also found this relationship. The friction force is equals to Ft2. So this negative needs to go. But remember what we said. Ft1 and Ft2 is just tension in the same rope. Are we clear? Ft1 and Ft2, this is tension on different sides of the pulley. But as long as the rope is the same, then the size of the tension is going to be the same. Therefore, it turns out that Ft2 is also equals to 8 newtons. Because the rope is the same. We're not talking about different ropes here. Are we clear?
Yes, sir.
So if Ft2 is equals to 8 newtons also, then since this relation here there's no negative, we can find out what the friction force is going to be. The friction force is going to be equals to 8 newtons. So here, friction force is just going to be 8 newtons. Remove this negative here. Now, we know what the friction force is now. The friction force is 8 newtons. We also know the normal force. The normal force we already found was 20 newtons. So we can rewrite our friction like this. The friction force Ff is going to be equal to the coefficient of friction multiplied by the normal force. Therefore, we can work out our coefficient of friction to be equal to the friction force divided by the normal force. And our friction force in this particular case is 8 newtons. 8 newtons, and our normal force is 20 newtons. So 8 newtons divided by 20 newtons, we're going to end up with a coefficient of friction which is equal to 0.4. Is that clear?
Yes, sir.
So this is how you work out the problem with what's this? You work out your equilibrium problem. Okay, 5, what does 5 say? Any questions? So in figure 5, the pulleys are frictionless and the systems hang at equilibrium. If FW3, the weight of the object on the right is 20, I have to admit someone. If FW3, the weight of the right of the object is 200 newtons, what must be the values of FW1 and FW2? We need to look at what this figure looks like. Okay. Okay. So this is what we have. Okay, this is similar to our equation number 1, to our example number 1, because in this particular system, in this particular setup, for us to do equilibrium things, in this particular setup, for us to do equilibrium things, we need to make sure that this point here, where the ropes, where this rope and this rope and this part of the rope, they meet, this part does not move. So remember, you always need to identify which part that is not supposed to move, or is supposed to be in equilibrium. So the part which is supposed to be in equilibrium in this particular case is here, this knot where these ropes are meeting. Are we clear?
Yes, sir.
Okay. So the next thing you're going to do is you draw an XY plane over this knot. You draw an axis, XY plane over this knot. If you draw an XY plane over this knot like that, so that this center, this knot becomes the origin. Now what are you trying to do? What you're trying to do is the following. You're trying to find out how much tension is in these ropes. How much tension is in the ropes? Are we clear?
Yes, sir.
Well, how much tension is in these ropes? Because the tension in each of the ropes is equal to the weight of these objects. That's why you're trying to find the tension. If you find the tension in this rope, that tension in the rope is equal to the weight of this object. If you find the tension in this rope, the tension in this rope is equal to the weight of this object. If you find the tension in this rope, the tension in this rope is equal to the weight of this object. The reason why it's like that is because these things are at equilibrium. These objects are not moving. They are stuck. They can't move down. They can't move up. Therefore, the only explanation for that to happen is that the weight of this object is equal to the tension. The weight of this object is also equal to the tension here. The weight of this object is equal to the tension here. This tension here is the same as the tension here. The tension here is the same as the tension here. Are we clear?
Wait, so could you repeat the tensions on the table?
We are saying that this setup is like this. Things are not moving because it's in equilibrium. And the reason why it's in equilibrium is because this point doesn't move. So this is the point you have to make sure that doesn't move. We draw our XY plane over this particular, you sketch an XY plane over this particular point here. So this side is going to be your positive x-axis. This side is going to be negative x-axis. Up there is going to be a positive y-axis. Down is going to be a negative y-axis. So we need to find what is the tension in this rope, what is the tension in this rope, and what is the tension in this rope. Once we find what the tension in this rope is, what the tension in this rope is, and what the tension in this rope is, it becomes possible for us to know what the weight is. The weight of this particular object, what is the weight of this object, what is the weight of this object. Because these objects are not moving. They are motionless. So if you have an object hanging from a rope, and that object is not moving, it means that the weight of that object is equal to the tension in the rope. Are we clear? Yeah, the weight of the object is equal to the tension in the rope. The tension this side of the rope, as we have seen from the other example, the tension in this side of the rope is the same as the tension on the other side of the pulley, even if these tensions are pointing in different directions. Here the tension is pointing up, here the tension is also pointing up. So the tensions are pointing in different directions, but they are the same. The tension in this side of the rope, this side, is pointing up, but it's the same as the weight of this object. It's the same as the tension in this rope. The tension in this rope here is pointing up. It's the same as the weight of this particular object. So what we do is we assign, since this is weight 1, we will call the tension in this rope FT1. Since this is weight 3, we'll call the tension in this rope FT3. Since this is weight 2, we'll call the tension in this rope FT2. Are we clear? Yeah, we'll call the tension in that rope Ft2. So when we do that, the other thing we have mentioned is that, if you recall, I'm just from saying, the weight of the object is equal to the tension in the rope. Now, what we've been given a piece of information where we are told if Fw3, the weight of the object on the right is 200 newtons. So one of the weights is known. The weight on the right is 200 newtons. The weight on the right is this one. So the weight of this object is 200 newtons. If the weight of this object is 200 newtons, then the tension pulling the object up is also 200 newtons. So the tension in this part of the rope here is 200 newtons. The tension here also is 200 newtons. Are we clear?
Yes, sir.
So Ft3, the tension in this rope, which is balancing the 200 Newton force, is 200 newtons. So Ft3 is 200. Ft3 is 200 newtons. The tension in this part of the rope is equal to the weight of this object. The tension in this part of the rope, this side, is the same as the tension here, is equal to the weight of this object. So if we can get the tensions, then we find out what the weights are. So here, so if you put our XY plane over here, we do our XY plane over here. So if you do an XY plane like that, so you have got this angle here. This is 35 degrees. Then there's something left down here. So that's going to be 90 minus 35 degrees. How much is that? How much is 90 minus 35 degrees?
55 degrees.
Huh? How much?
55 degrees.
65? Okay. So, to make things easier again, as you can see, it will be necessary to make a correction. So we are going to say the following. For Ft3, which is the tension in the third rope, for Ft3, you're going to have Ft3 cos, not sine, Ft3 cos 65 degrees, which is the same as Ft3 sine 35 degrees, basically. So you write Ft3. The first thing you're supposed to do to make things easier, you put an XY plane over this point. You put an XY plane over this point. Then using this angle, you find what the angle is between this rope and the XY plane, which is supposed to be your 65 degrees. Are we clear?
Sure, sir.
Yeah. So you do that. You make that sketch. So I also need to make that sketch so that we don't have this confusion here. So you're going to end up with Ft3 cos 65 degrees, which is going to be equal to 200 newtons cos 65 degrees, which you're going to find in this case, if you say 200 newtons, if you have a calculator nearby, 200 newtons times cos 65. Okay, 35 or 90 minus 35. What did you have? So 55. So 55 degrees. So 200 newtons times cos 55 degrees. You're going to find is the same as what we have here. You try it with the calculator. So I have 115 newtons, but if you do 200 newtons cos 55 degrees, it will give you 114.7, which is roughly just 115. Are we clear? So make the correction. Those of you who have printed the notes, you write Ft3 is equals to Ft3 cos 55 degrees equals to 200 newtons cos 55 degrees, which will give you 115. Then you move on to this other bit, Ft3 sine 55 degrees, that's going to give you 200 newtons sine 55 degrees. So 200 times sine 55 degrees you're going to get yourself 163.8, which is just 164 newtons. Are we clear?
Yes, sir.
With that in mind, since we have drawn our XY plane over this, so the XY plane should be there. Put the XY plane. So the angle this rope makes with the positive XY plane is 55 degrees. Then there will be the angle which this rope is going to make. The angle which this rope is going to make is going to be 90 degrees plus 50 degrees. Is that clear?
Sure, sir.
That's the angle which this rope is going to make with the positive x-axis, this side. So 90 degrees plus 50 degrees, that is 140 degrees. So we move on to find the tension in this rope. The tension in this rope, which is going to be our FT2, the tension in that rope is going to be, so scrap off this. Scrap off the negative, which is our FT2. Our FT2 is going to be equal to FT2 cos 140 degrees. So you scrap off this, it's going to be FT2 cos 140 degrees. Now the FT2 we do not yet know, but 140 degrees, cos 140 degrees, if you do that cos 140 degrees, you're going to find that cos 140 degrees is minus 0.77, which is what we have here. So the way the answers this side, they are correct, but I'm not happy with the way I did them. This is stuff I did last year. So there has to be a better way of doing things. So I need to make serious corrections to this by placing the XY planes over these particular points I'm interested in, so that I can clearly indicate which angle is how much and stuff like that. So here, remove this negative. It is FT2 cos 140 degrees, and that's what's going to give you minus 0.77 FT2. Are we clear?
Yes, sir.
Then you move this side, you're going to have FT2 sine 140 degrees. FT2 sine 140 degrees, sine 140. Sine 140 you're going to find out is it's going to give you 0.64 FT2. Are we clear?
Yes, sir.
Then you move on to the first rope. This rope here. With your XY plane drawn like this, you notice that if this is your positive x-axis, then this rope here makes an angle of 270 degrees from the positive x-axis, from this side. It lies at an angle of 270 degrees. Is that clear?
Yes, sir.
So we pick that angle 270 degrees, then we are trying to work out the tension. So the tension in FT1, so FT1 you write on top of this, if you've printed the notes, you're going to write FT1 cos 270 degrees, that is going to give you 0. So on top of the 0, you write FT1 cos 270 degrees, that should give you a 0. Has that been done? These notes, especially these particular notes, if you have not printed them, because there's a lot of corrections which need to be made. But the corrections are minor, it's just that it's failing to compile. Okay? So if you have not printed these notes, print them. Then as we're going through them, you make the necessary corrections which need to be made. Okay? Then this side, you're going to have, on top of this, you're going to have FT1 sine 270 degrees. That's going to give you minus FT1. Are we clear? So FT1 sine 270 degrees, sine 270 degrees is going to give you a minus. So this one is supposed to be minus FT1. So can we make that correction? Has the correction been made?
Yes, sir.
So now that we have done that, we can find out what our tensions are. We add the x components. That's going to be 115 newtons plus minus 0.77 ft2 plus 0 newtons. When we do this, we will find our ft2. So it's going to be with 115 newtons plus minus 0.77 ft2 plus 0 newtons. And when you do that down here, we'll end up with this. We end up with 0.77 ft2 equals 115. Then we divide both sides by 0.77. We end up with ft2 equals to 115 divided by divided by 0.77. So we're going to end up with ft2 being equals to 149 newtons. So the tension in the second drop is going to be 149 newtons. Now remember what we said. If the tension is a certain amount, then the weight is going to be the same amount. So the tension in this rope is 149. The tension this side is 149. Then therefore this weight, since it's not moving, also is going to be 149. Are we clear?
Yes, sir.
Then we move on to the y components. When we move to the y components, we are adding this 164 newtons plus this 0.64 ft2, then plus minus, this is the minus, this is minus ft1. So when we do that, when we add those bits, we are going to have so it looks like here I made the correction properly here. So you're going to have 164 newtons plus 0.64 ft2 plus minus ft1, which is equals to 0. We are looking for this. We already know what this is now. This is 149. So ft1, when you take this bit to the other side, you're going to have ft1 equals to 164 newtons plus 0.64. Then this bit you have found, it's 149, and you're going to end up with ft1 equals to 260 newtons. So if the tension in the first drop is 260 newtons, then it means that the weight is also equals to 260 newtons. Are we clear?
Put a question, sir.
Yes.
On taking the degrees, we take from the x positive axis.
Yes.
But there on the second for FW2, why did we use 50 instead of 50 plus 9?
No, you are late, I think. You have not been following. You didn't use 50. We said make corrections. This negative is not supposed to be there. It's supposed to be ft2 cos 140 degrees. Are we clear?
Okay, I understand now.
ft2 cos 140 degrees. This side ft2 sine 140 degrees, so that you get this. You get this. Here is supposed to be ft3 cos 55 degrees, 200 cos 55 degrees, so that you get this. ft3 sine 55 degrees, 200 sine 55 degrees. So you're supposed to make corrections. That's what I've been asking people to do. I've said people should print these notes so that as we go through them, people should make corrections, because there's things which, yes, some of the things are correct, but some of the things are not very clear. I'm always about trying to make these things as clear and as simple as possible. The way they are, it's not very clear. Okay, that's why I'm saying correct. Instead of this, write this. I've also said draw an XY plane over this particular point, so that this side becomes a positive x-axis, this side becomes a negative x-axis, up here becomes a positive y-axis, down here becomes your negative y-axis. That XY plane should be very clear, because we'll be measuring angles from the positive x-axis. Over every object you're interested, you draw an XY plane over that particular object. Are we clear?
Yes, sir. Clear.
Yeah. Any questions? Same thing applies to this example here. Now, this example I think is better than the other example which we didn't look at, because we needed an angle like this. But even in this particular case also, what you do is over the object you draw an XY plane. So the object is moving this direction like that. So you draw an XY plane like this, where parallel to the incline, that is your XY plane, that's your X axis, perpendicular to the incline, that is your Y axis. So you draw an XY plane over this guy, you also draw an XY plane over this guy, so that you can find your components, the components which you need to find. Is that clear?
Yes, it is.
Yeah, so we have run out of time. Unless there are any questions, so we'll continue. We're halfway through. So when we meet, we'll continue through this particular problem. Yeah. You have good class coming up?
Yeah, different teachers who have some.
Okay, fine, yeah. So we'll continue next week. So next week when you meet, you continue from here. So again, I'm asking people, you draw an XY plane over these. Okay. Now with this particular object, when you draw an XY plane over these, this is the same as what we have here. This is same. Use this as a guide. Use this as a guide. Use what the problem we couldn't work out, remember? We can still use it as a guide for what we want to do and what we needed to do. This. So remember what it is. You draw an XY plane over here like this. This is your X axis. Then your Y axis is going to be like this in this particular direction. So your X axis, that direction, your Y axis in this direction. When you do that, this particular object is supposed to move in this particular direction. Now, when you have an object on an incline, you choose the direction in which the object usually is supposed to, if the object is not stopped, it will move downwards. So the downward direction, this side, is what is chosen to be the positive x-axis. The upward direction is what's chosen to be the negative x-axis, and the up is what's chosen to be positive y-axis, and down is what's chosen to be the negative y-axis. Now, if this angle is known, like in our example, the angle is 35 degrees. If you move from here, round like that, up to where this weight is, the direction of the weight, you're going to see from here all the way up to this line here, that's going to be from here, go up to here, that's 90. You reach this side, that's 180. You reach here, that's going to be 270. But if you know how much this angle is, for you to find out the whole angle from the positive y-axis going round like that up to here, it's going to be 270 plus this angle theta. Are we clear?
Yes, sir.
It's 270 plus theta. So theta needs to be known. So in this particular example here, we should have given what theta was. For example, if it's 30 degrees or 35 degrees, so that you can find out what the angle is. 270 plus theta. So using that angle 270 plus theta, you'll be able to find out what is the x component of the weight, what is the y component of the weight. Then everything else comes out nicely. You find out the y component of the weight in this direction. That's going to be 200 times whatever. If let's say this angle is 30 degrees, so it's going to be FW, which is 200 cos 300 degrees. Then the y component to be 200 sine 300 degrees. Then you get that, and everything else just gets resolved. So even in this particular example here, where we are here, where is that? Here. You need to draw an XY plane over this particular box. Draw an XY plane, sketch an XY plane, print the notes. You draw an XY plane over this in this direction, you draw another one in this direction. The weight of the box is going to be in this direction. That weight makes an angle theta. That thing theta is the same direction, so you can work out what the whole thing is. Okay. All right, so see you next week on what is on Monday.
Thank you.
All right.